Hello, biology students. I want to do a quick review of some ecology concepts, especially those of carrying capacity, um, and what happens if there are some environmental conditions that occur that cause a population to get very small, called a bottleneck. And so let's move on. So in this activity, or at the end of this, hopefully you have a better idea of what this term carrying capacity means. Um, and then you can actually use a graph to make some predictions about environmental changes that might cause, excuse me, an upward or downward trend in the carrying capacity chart that I'll give you some examples. And then finally, that you can determine or identify or kind of understand the ideas of carrying capacity, overshoot, equilibrium, which we've actually already kind of seen this term of equilibrium. This happens a lot in science, of things staying in balance. Think of that equilibrium as a little bit like homeostasis. A bottleneck event, founder effect, and then competition. All right, so let's jump right in with a sample carry capacity graph. Not overly difficult to understand. They're always going to be something over time, and so let me also talk about this word population. So if we're talking about population, I mean, if we talk about the population of humans on Earth, we're about 8 billion humans on Earth, and some people would argue that that's higher than our carrying capacity of Earth. Actually, can we keep getting more and more and more people and keep supporting those individuals with food and shelter and things like that? Um, uh, so population, just how many of a species, and so the idea of species is one specific type of organism. So the population on Earth isn't all the animals added together, it's the population of humans. If we talk about humans, I could talk about the population of black rhinoceroses. I think black rhinoceroses are down to about 1,000 individuals on Earth. So just give those ideas of population and species. Now, if we want to talk about the entire ecosystem, that would be something a little different. But carrying capacity is just talking about a single species in an area. And we can also think about carrying capacity as being a small area or a large area. As I give my example of carrying capacity of Earth, for humans, and can we sustain 8 billion people? Or I could just talk about carrying capacity of a smaller area. So let's suppose that this chart is showing us the population of, I don't know, let's suppose Canadian geese in the United States. And when it says in millions, that just means that this would be 0.5 million, 1 million, 2 million. So sometimes charts will do that just to give you, make it so it's not as big over here, so the numbers aren't quite as large. And let's suppose this is between 1800 and 1925. So what we're really shown here is that at 1800 there weren't any of this. So again, I don't know, this is just made up information. But let's suppose that this were for Canadian geese. And the first Canadian geese entered the United States in 1800s, and they shot way up. And they grow really quickly because there's not any competition. Generally speaking, when we get a new species that is introduced, there probably aren't anything that are going to eat that organism. And that's why invasive species can sometimes be very dangerous, because there isn't anything to control their population. So they'll grow, 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 grow. They'll actually go beyond what the environment can actually sustain, because they're reproducing so fast, there's no checks and balances, so to speak. And we'll get this idea of overshoot. Overshoot just means that we'll go up and we'll go over what we can actually handle, what the population, what the resources in the ecosystem can sustain. Um, and then we'll get this fluctuation, and this is pretty natural for things to kind of fluctuate up and down. Just that's just the laws of nature that happen. So you'll sometimes you'll have good years, sometimes you'll have bad years. But if we want to think of this carrying capacity, we kind of think of the average of all these ups and downs. So if I were like estimating the carrying capacity of this population, I would gonna kind of go up, and I'm gonna kind of cut these ups and downs in half. I'm gonna come over, and I'm gonna be like right here. So if I were to guess that, maybe I'll say 1.6 million is the carrying capacity of this species in this ecosystem. So, and it can go up, it can come back down. Sometimes it can go down drastically and then stay leveled back out. So let's suppose this population goes up, it stays pretty level, but then it goes down a little bit and it goes across. So now something killed off a population. It had decline. There was more deaths than births, and then it leveled out again. Now that carrying capacity, or sometimes what we call equilibrium. So this is in a new equilibrium. I'm not going to write out the whole thing because my marker doesn't do real well. And so, what might have happened here? Well, maybe they lost some land. So maybe something happened where, there's now less land for those animals to live in, or there's plants, or whatever it might be. And so this is the new normal, so to speak. So this is a new carrying capacity, between, 1900 and 1925. What else might have happened? Well, maybe we introduced hunting. And so really hunting, when we have deer hunting or we have turkey hunting or any kind of animal hunting, we've deemed that necessary to control the population so they don't overgrow and use up their resources. We don't want the population of deer or any other animal to be in stress. We don't want them to be, if there aren't enough resources, then the herd won't be healthy. And so hunting is really a way of trying to keep the herds healthy, so to speak. Let's see. So yeah, that does a pretty nice job. So this overshoot is important to kind of go up. The carrying capacity is kind of this average. It can go up, it can go back down, and we'll talk about some reasons why in the next slide. So what are some reasons that and a lot of this is actually, to be honest, is a little bit of common sense, or at least it's logical. What might increase the carrying capacity? No, I've already mentioned a couple of these. Increased availability of habitat. So maybe the land is, you've gotten more land. So let's suppose this is a national park that maybe got bigger. They brought more land into the national park, which generally that's going to eliminate more hunting, or that's going to at least provide a more available land to live. But really, when you get down to it, and this is the the crux of things. Oops. It really gets down to resources, because land could be a resource. So, do you have food? Do you have water? Do you have land to mate in? And so those things will increase the carrying capacity. If it's really good year for food and water, lots and lots of rain, lots and lots of things to eat, then you're going to be able to reproduce more, and more of your offspring are going to survive. We could also say a decrease in the competitor population. So if there's something so let's suppose that we are the competitors. Suppose we banned deer hunting. Then the population of deer would increase over time. And now it may not be a healthy population, but it would definitely increase over time. Now there do seem to be more things that could then decrease the carrying capacity. So what might cause it to go down and have a new normal? Well, it's kind of the opposite of a lot of these things. So we're going to decrease the availability of resources, whether that be food, we call that a famine, a drought, the less of water, or maybe we lose land. Now, this loss of land could be something like deforestation, as we're cutting down trees and there's less land for the animals to live in. This has been one of the biggest changes that man has made to Earth over the last, let's say 150 years, is that we've cut down a lot of the rainforests, and by losing rainforest, then the population of animals that lived in there certainly has to go down because there's less rainforest for them to live. Could be an increase in the competitor population, and I'm not sure I spelled competitor right actually. So actually I might have, because it didn't underline it. But so if we increase the number of competitors, or we introduced one, remember when I said before, let's suppose that here we introduced some species that didn't have a competitor. Well, when the line went down, maybe we introduced something that would then eat those, or that would hunt those and bring it back to a more reasonable level. Maybe we thought that 1.6 million were too many Canada geese, so to speak, in my example here. So we did something to bring those back down. And that is one of the reasons why Canada geese have reproduced so greatly in the United States, because they're not native of here. There is nothing that hunts those, at least to a great extent. There's no natural predator in the United States, at least in our area. Sorry, back to this. So with increased predators, Disease can bring things down. So there can be a disease that's introduced. So really, if we think of COVID right now, COVID is a new disease in our species. And in the last year plus, 3 million folks globally have died from that. So that has actually brought our, I can't say the overall population of the Earth has decreased, but in certain areas it actually has. And so disease can be a great equalizer, so to speak, of populations. And then finally, can be just a catastrophic global event or a regional event. So let's suppose that there's a large volcano, and that volcano can, for a certain ecosystem, can bring the population down because it can damage the ecosystem. It can kill organisms. So maybe a volcano. This is what did in the dinosaurs. That was a global event. And so, speaking of the dinosaurs, that asteroid, and so it's most popular today that asteroids are actually an asteroid fell and caused some a massive one, the size of Mount Everest. It was mountain sized and caused some crazy amount of damage. Catastrophic global events could be us caused. It could be when we were doing a lot of nuclear testing back in the 40s and 50s, we were very worried of a global catastrophe. In some local areas, there were global catastrophes where there was fallout. So there can be nuclear meltdowns that can, in a certain area, can affect the population. But generally speaking, big catastrophic global events um, are few and far between. There could be fires, and that's a lot of the asteroids. The asteroid actually caused a lot of global fires, and we know there was a little thin layer of ash all over the globe because there was a lot of fire going on at that time, and that's obviously destroys habitat and other things that we have here. So um, we don't often think of a global event of an earthquake causing any kind of an event like this, maybe on a very, very small level, but generally speaking, we want something that's going to change the ecosystem vastly. Okay, let me give you an example of something now called a bottleneck or a genetic bottleneck. Now, if you think of a bottleneck, if you think of like an hourglass, and an hourglass, I'm going to kind of draw onto hourglass here. I'm going to try. So here's an hourglass, right? And this the sand is up here, and the hourglass goes through, but it only goes through very, very slowly because there's a very thin neck here, and that's actually what referred to as a bottleneck. And that example, the name actually is a pretty good example of what we're looking at here. What we're talking about, and with a genetic bottleneck, meaning like the genetic variability. So right now in the United States, we have a vast genetic variability of humans, and so we have a very healthy population. We have lots and lots of different genes. We are not all related, so to speak. However, if there was some sort of event, so this example we give here is a cheetah. So we feel that over the population, so there are three different examples here. So here we're talking over 100,000 years ago. So this is showing the variety of cheetahs. And so the variety of cheetahs were great. There were lots and lots of cheetahs. They were not related whatsoever. So we didn't have anything called inbreeding occurring. Inbreeding, and so inbreeding is whenever you're mating too close to your relatives. But there was a catastrophic event that happened about 100,000 years ago, and so this event might have been a who knows? It could have been a global event. It could have been an ice age. It could have been, however, the ice age is going to be a little bit here. So this might have been the beginning of the ice age. And so what happens is lots of your population die, and all of a sudden, if there are only a few species left, so of your species, so let's suppose we went from, and this second one gives a better example. So they survive if they don't. So if the bottleneck goes all the way down and nothing gets through that bottleneck, that's extinction. So bottlenecks can cause extinctions if none of the species are able to survive that event or can get through that time, so to speak. Think of it as time passing through the neck. So the population did survive, and so it recovers. It gets bigger and bigger and bigger. Then there was another event about 11,000 years ago. This is at the end of the Ice Age. The mammals, when a lot of the large mammals on Earth actually became extinct. So this is when woolly mammoths went away and saber-toothed tigers went away. And a lot of the big mammals on Earth started to die off. And a lot of it was actually hunting from humans because we were starving for food, to be honest. And so we were able to hunt those things. Scientists think that as few as seven cheetahs survived in Africa. So if we think of those 7 cheetahs that were surviving this bottleneck, they were probably all related. And if they weren't related, they were so far apart they could have never reproduced because they would have never found each other. So this might have been a very small pack that survived. And notice now that they've survived the bottleneck, notice over here, there's less variety because there's only kind of these there's 2 different colors, the green and the beige or the tan ones. Over here we had variety. We have blue and we had this kind of this orangish color. So there was lots more genetic variety or variability. Some of those died off and only a few survived. And so these are all family members. And so it's a sort of a way of resetting evolution in a way as well. We are worried that today we are actually under another bottleneck because today the population of cheetahs are less than 8,000. And so we're really worried. And again, it's loss of habitat and whatnot. So we see bottleneck with other species. As I've mentioned, the black rhino. Today there are less than 1,000 black rhinos. And in fact, it may even be less than that, maybe in the hundreds. It gets to a point where we know that species can't survive anymore because of inbreeding. Now, I do want to real quickly here talk about founder effect. So founder effect, when you find something, or if you're the founder of a university, you begin a university. So like the founder of Danville got to name it. So that was where we get Danville from. I think his first name was Daniel. I think that's where the idea comes. But he founded. So when we find a founder effect, what we're really referring to here is that a species kind of re-jumps, it restarts, because there was only a very small number of cheetah that actually began that species evolving forward or moving forward. And so we call that the founder effect. So bottlenecks can lead to founder effects when a very small group of organisms then kind of begin the resetting or the recovery of that species. And it can lead to evolution because inbreeding can then cause mutations. And so that founder effect kind of goes along with mutations and inbreeding as well. So hopefully that helps a little bit with that concept. Really quickly here, I want to talk about the bottleneck effect and that founder effect a little bit and give you another graphic. So here's an example of, now this is really tiny, but here's a list of a whole bunch of dinosaurs. So this is a chart that showed a bunch of different dinosaurs that lived on Earth, and here's the mammals. Now, when the dinosaurs were the peak of the dinosaurs about 65 million years ago, so 65 million, the animals that ruled the Earth were dinosaurs. Then that big rock fell out of the sky and caused some pretty severe damage. Any of the big dinosaurs died off. They were unable to survive because of a loss of resources. Now, the mammals that were around were extremely small. We're talking mouse size or even smaller. And so they needed less food. They were more able to adapt. And so what got through this bottleneck? Well, what got through there were all the mammals, so that the mammals that evolved into what we have today. And also what left were birds. Now, also, there were other reptiles and things that got through, but birds are really the result of of the dinosaurs that existed today. We actually think that dinosaurs were, in the end, more like birds than they were reptiles. They had a 4-chambered heart like birds have, where reptiles only have a 3-chamber. We know that some dinosaurs were starting to evolve feathers. And so today's birds are really what left over. So not necessarily crocodiles. A lot of people would think of the crocodiles or the leftover dinosaurs. Not necessarily. It actually are the birds that are around today. But this bottleneck, so the populations would have bottlenecked down. They would have shrunk populations, and only a few got through. And then once they got through, and that event, so for instance, like the meteor, the Earth kind of went back to equilibrium after many hundreds of years of destruction. Then there can be this another like rejuvenation, and so that we get this big event of evolution. Species can start reproducing again, and kind of Earth can go back to a new equilibrium. But this is an example of that founder effect. So the birds that are around today are just those few dinosaurs that survived and got through this little bottleneck. So hopefully that helps with that concept. And lastly, I just want to talk real quickly about predator-prey relationships. So the idea here, this is an example, a pretty famous example of a hare. So snow hare, snowshoe hare. So it's a rabbit, kind of rabbit, and then a lynx. And so if the population of the shoe hare is the prey, lynx is the predator. So up goes the number of rabbits, then a little bit later the upswing in the lynx, because it follows a little bit behind because it needs food. So the food reproduces, and in fact the rabbits would reproduce more quickly than what the lynx would, just because of the more pups, or more, I don't know what you call a baby rabbit. I actually don't know what a baby rabbit is called. Probably should know that. So it reproduces, then followed behind would be the lynx. Then the lynx get to a certain point, and then the hares start to decrease because they're hunting a lot of them. And then followed a little bit behind, then the lynx population will have to go down because the population with food is going down. They'll reach kind of a bottom level, and you could almost kind of think of this as kind of that carrying capacity. Then we'll go back up. The rabbits will go back, and then the lynx will go back up, and we get this cycle of up and down and up and down. But definitely the prey, this population will increase ahead of the predator. The predator kind of lags behind, we say. Okay, so thanks for listening. I have a few questions, and there's also a hard copy of a carry capacity graph that, if you want that, it's in the quizzes later. But if you also want to have a hard copy of that, I would understand it's a little easier to look at. So thanks for watching. Please do your best on the following questions. Thanks.